We have a short week this week, just a few days. We're out Thursday and Friday, and then next week, after spring break, we'll come back Monday, and we'll have a review for the tests, and then on Wednesday we'll have our tests, which will cover chapters 4. So we finished off with chapter 4. Did we do chapter 3 on the last test? I forget. No, 3, 4, which sort of run together. And then we're going to have the first part of chapter 5. Basic stuff about magnets, sort of grade school stuff. North, south poles, opposites attract, that kind of thing. And then sort of basics about the Earth's magnetic field. And then we'll also do the force on a charged particle traveling in a magnetic field. That's already going to be the cross product. We've seen the cross product before last semester. Remember we did it with torque. It's when we want to take two perpendicular vectors. And so it'll be a pretty basic problem. Just I give you a charge moving through a magnetic field, and you tell me what its force is. You just have to do the cross product for two vectors. And I'll show you that before we have the test. So there are 1 or 2 homework questions. I think just 1, but we'll do a couple practice problems in class. Okay? Make sure you do the homework for chapter 4, because a lot of those homework problems be similar to what you see on the test. I'll say a lot, you have 4 or 5 questions. So. But you'll see a multi-loop circuit, you'll see a combination circuit with resistors, that means in parallel and series. You'll see those features of your household, the safety features, probably like a free response, but you'll certainly see a free response, just not in a free response problem. You're going to see RC circuits, similar to what we did, pretty simple. I give you a certain time, I ask you for the charge, current, voltage on the capacitor, or in the circuit at that time. Okay, so I'll go through that homework pretty carefully. And let's continue on with chapter 5. So the first part of this chapter is pretty basic about magnets and what magnets are and how they work. Just a few basic things about magnets. They have poles. And we call these north and south poles. You've seen a bar magnet, I'm sure. A bar magnet has a north and a south pole. If you have these poles, the like poles repel one another. Opposite poles attract. Did y'all have the little Brio train sets when you were a kid? The magnetic Brio train sets? Did you ever like to put the like poles towards one another and you'd push it along and then scoot out ahead of it? Yeah. Okay, so opposite poles attract. That means if I take 2 magnets, north, south, south, north, like this, these 2 magnets are going to feel a force that is opposite. And likewise, if I have opposite poles, where I have, say, a north and a south, they're going to attract towards one another. And then the other thing is that monopoles do not exist. People used to think that monopoles did exist. They thought, well, if I have a magnet and I break it in half, then what they would get is that they would get 2 little magnets with, north and south poles. Well, they thought if I keep breaking it in half, then eventually I'm going to get just a north pole and just a south pole. Because they didn't understand where magnetic fields came from, that seemed like a logical conclusion that if you keep breaking this thing down, eventually you're going to get sort of the fundamental particle of magnetism. But magnets are created by moving charges. And electrons, which are always moving, create a magnetic field. And so the result of this is that no monopole can exist, because as you break that thing down further and further, eventually you're just going to get to an electron, and it has its own magnetic field, or an atom, if you will, and it has its own magnetic field, and so you can't, because it has its own magnetic field, you can't split it into a plus and a minus. So imagine if I have an electron right here, it's buzzing about, so it's going to have a north and a south pole. It will generate its own magnetic field, And so you can't create a monopole. You can't keep breaking those magnets down piece by piece until you get a monopole. All right. We talk about magnetic domains when we talk about magnets. A magnetic domain just describes a region of uniform magnetization when a group of electrons are oriented such that their magnetic fields are all in the same direction. So I'll show you on the next figure, I'll show you magnetic domains sort of as they're spread throughout. But if you imagine that if I have these electrons and they have magnetic fields that are all in the same direction, these are their magnetic field vectors, we would sort of call this little region a magnetic domain. It's just a region within a material where all the magnetic fields of the electrons are aligned. And so if we look at a permanent magnet, it might look something like this, or rather this is not a permanent magnet. In most materials, the magnetic domains are oriented randomly. So each of these little sections, these are the electrons. They have their magnetic fields all aligned in this little region of space in this material, whatever this material is. But if we look at the magnetic domains of all of the electrons in that material, then they're going to be just distributed randomly. So like this would be, for example, I don't know, your body. Like most of your body is non-magnetic. You have electrons, of course, and so you have a magnetic field, but the magnetic domains are all oriented randomly. They're not lined up. And that gives you a net magnetic field of 0. And so here, my net magnetic field, it's a vector, is equal to 0. This is the variable that we'll use for magnetic field. And I'll give you the units for that in just a bit when we actually calculate what the magnetic field is. All right, in a permanent magnet, those magnetic domains are all lined up. And so you get a net magnetic field that is in a particular direction. You can get this in a couple different ways. In permanent magnets, naturally occurring permanent magnets, you have a volcano that will spit out these molten metals, and then those molten metals will solidify in the Earth's magnetic field. So if you imagine the Earth has a magnetic field, say it's in this direction, and then you have a volcano like this. It spits out lava. That lava flows down, and the materials that are in this lava, their magnetic domains all get lined up in the same direction. When it's molten and hot, those magnetic domains, you can think of them as malleable. They can change direction. And when they line up in the Earth's magnetic field, it'll cause all those magnetic domains to line up. And then when they solidify, it's like they're locked into place. And that's how you create permanent magnets. You can do a similar thing in the lab. Or you can also use electromagnets. Electromagnets use an electrical current. To create a magnetic field, and then that aligns the magnetic domains of the material. If you just have a wire with no current flowing through it, then there's no magnetic field. But if we have a wire with a current flowing through it, yeah. Sure. So if you have a wire with no current through it, then there's no magnetic field. But if you have a wire with a current through it, whether there's a piece of material through it or not, so even if I just have a wire like this with nothing going through it, if I have a current through it, then there is a magnetic field. It generates a magnetic field. Have y'all ever made a magnet? certainly done this before, right? Where you just take a nail, wrap a piece of wire around it, and hook a battery up to it. Did that first grade? You did it in first grade and you forgot it? Yeah, that's far away. You just forgot it maybe from first grade. But you take a nail, you wrap a piece of wire around it, and you can pick up things like paper clips and stuff like that. Let's see. We will revisit your first grade class if you like. I have a video here to show you if you want to, since y'all didn't have that. Let's see, where is it? Oh yeah, that's it. Thank you. Thank you. Create an electromagnet. It's the same idea behind in junkyards when they pick up, the big thing that picks up the iron. It's the same idea. All right. All right, let's try these quick tests. Oh, by the way, did we finish the concept test from the back of the book for chapter 4? Somebody tell me that. Beams? We did. Okay, great. Thank you. All right, let's try these. Which of these reasons best describes why some materials are permanent magnets? These are so-called ferromagnetic materials. Let's do about 10 more seconds. Stop at 35. Okay, good. B is right because their magnetic domains are all aligned with one another. So B is the correct answer there. And then which of these explains why a permanent magnet is magnetized? All right, I'll stop at 25, 25. I'll go on to 30, 30. Okay, again, B is the right answer here. Let's see, somebody put A having a current through it. That's not correct. If I ask the question of why is an electromagnet magnetized, it would be because of the current. That the moving charges in the current actually generate the magnetic field, and electrons produce their own magnetic field. That is true, but everybody has electrons, and so if that was true, if that actually what causes a thing to be magnetized, then we'd all be magnetized, and it's like we all walk around being attracted to one another or loving one another, because we all have electrons in us. But really the reason is because these magnetic domains are not aligned in this. They're all the permanent magnet, they are aligned rather. Okay, I would expect some multiple choice questions just about the basics of magnetic fields, north, south poles, opposites attract, likes repel, all that sort of thing. Basic idea of electromagnets. Later, after this next exam, we'll get into electromagnets and we'll actually begin to calculate the forces and the fields that are associated with them. All right, we also use magnetic field lines to represent the strength and direction of the magnetic field. And again, I'm going to use B here to represent the magnetic field. It is a vector quantity, as we'll see. We'll have a couple of rules. These are similar to what we had for electric field lines. So are these on the next page? Yeah. So a couple of rules. First of all, magnetic field lines start at the north pole. and end at the south. So they start up here, and then they go into the South Pole. They terminate at the South Pole. And then the second thing is, just like we had with electric fields, is the density of the B field lines. Gives the magnitude of the B field. Just like we had with electric field. So let's try this. Let's say that this is option A, this is option B, and this is option C. Where is that magnetic field greatest? At A, at location A, B, or C? Where is the magnetic field greatest?
B.
Yeah, click it.
Oh, how embarrassing.
All right, just a few more seconds. I'll stop at 25, 25. All right, good. B is right. Do you know what happens when a pencil, when a clock gets hungry? It goes back for seconds. You'll get it secondhand on the clock. Okay. All right. So field lines are very much like the field lines we've been using. They will actually be used to describe a force. We're not going to really get into the field lines and the forces, but or at least we won't use them in the same way as we did the electric field lines. But you do need to know the basics about the field lines. They go from north to south. This magnitude gives the density. Unlike with electric field lines, where we sometimes had the field lines would go off into infinity. So remember, like if we had, say, two charges plus 2q and q, and negative q rather, remember we would have this situation where I would have these field lines that go off into infinity. You can't have that with magnetic field lines. Why is that? Why can you not have that with a magnetic field line? Right, for both of you. So, yeah, so I can't have twice the North Pole as I have for the South Pole, whereas here I have twice the charge here. So it goes back to that idea that I can't have a monopole, that I can't isolate a North or a South Pole. All right. We're gonna skip the PhET. No, let's do it. I'll go ahead and show it to you. It's kind of y'all don't do the PhET simulation in lab, do you? Have y'all done the magnetic fields lab yet? Right, where you measure the Earth's magnetic field. Yeah, y'all didn't do the PhET. Okay, let's pull it up. I think this will work. Let's try. This looks new to me. You can look this up later, but this just shows the. Oh, I'm sorry. What happened over here? Has that always been off, guys? I'm sorry. I think that we've lost our bulb. Oh no, there it is. Okay. I'm sorry. Y'all should have said something. Y'all can see this over here? Not real great, right? I'm sorry, y'all. Okay, so here you can see the magnetic field. You can flip the polarity. Notice it changes the direction of the things. You can see the magnetic field inside of the magnet. Here we can move the compass around and see how the magnetic field changes. See if I can show my lines. No. We'll get to this later. This is the Earth's magnetic field. Notice that on the Earth, that if I think of the Earth as a bar magnet, the south pole of that magnet is up here in the northern hemisphere, and the north pole of that magnet is down here in the southern hemisphere. We'll get to this, and you need to know that your magnetic poles for the Earth are flipped from the geographic poles. And it sort of goes back to how we define what is the North Pole in a magnetic sense, but we'll come back to that. Anyway, if you can play with this. Oh, here's an electromagnet. You can change the number of loops, and we'll get into this. That is the number of turns a wire. Let's change it to 7. I'll say that you can change it. Okay, I guess not. Anyway, we'll come back to this and how this works as a solenoid switch, and how when you change the number of loops in it, it changes the magnetic field. And we'll look at how a solenoid switch works later. Okay. Let's look at the Earth's magnetic field. Compass's needle has a magnet with a north and south pole, and the north pole of the needle points to the north, and the south pole of the needle points to the south. And so if you imagine that the Earth is like this big bar magnet. Oh, have y'all ever done this? Have you ever taken just a magnet? You can create a compass out of magnet. You can just take a little block of wood and put it in a bucket of water and put your magnet on top of it, and it'll rotate freely within the Earth's magnetic field. And so if you're ever out, I don't know, in the woods or whatever, and you need to know the north or south, just pull out your bar magnet and put it on a piece of wood in a bucket of water, and then you have a compass. Yeah. Dr. Baker used to do that always, because he did cool stuff like that. Most of y'all don't know Dr. Baker, do you? You have? Yeah.
He's got to do that, just like a needle, they have like a static charge, stick it on something that's close.
Really? I've never seen that happen, so, yeah, it'll be pretty cool. Or you can pull out your rainbow knife with a little compass on the top. I have one of those when I was a kid. Y'all have that? When you open it up, it has matches and stuff in it, and a little table saw. I don't think rainbow is quite as popular. All right, so anyway, the point is here that if I think about the Earth, that if this is the Earth, right, North America is here, South America, there's Europe, Africa, that the northern geographic pole is up here, but that is the southern magnetic pole. That they're flipped from one another, but if I think about a magnet in my compass, the northern pole is going to point towards the southern magnetic pole, which is the northern geographic pole. They're flipped from one another. And the reason we call it that north pole is because the north pole of this magnet points towards the northern geographic pole. But that's really the southern magnetic pole. Y'all follow me on that? They're flipped from one another. We can have variations within the Earth's magnetic field, and y'all saw this with the magnetic field experiment where you actually measured the magnetic field here. But if you go online, you can figure out what is the magnetic field at your particular zip code or your particular address, because it changes depending upon where you live. It doesn't change that much around here. Why is that? Why is the magnetic field actually fairly constant here? There's no ore there, no iron, no deposits of magnetic materials. Let's watch this little clip. Y'all seen, what's it called? Without a Paddle? Y'all seen that movie? Did you think it was funny? Okay. Okay, well, that's because they all produce their own magnetic field. The Earth's magnetic field can change in different places. All right. The Earth's magnetic field is also important. Oh, let's try this quick test, actually. Which pole of a magnet points towards the magnetic north pole, the Earth's magnetic north pole? Which pole of a magnet points towards the magnetic north pole? Let's see, I'll stop at 35. 35. That is right. So the north pole points towards the magnetic south pole. Remember, think of our Earth. This is the northern pole up here, so we have like the Arctic, and here's Antarctica. If we think of our magnet, we have the north pole that points up here, which is the northern geographic pole, but it is the southern magnetic pole. northern geographic, but the southern magnetic pole. They're switched from one another. So if I think of my bar magnet, it looks like this, south, north, like that. All right. The magnetosphere also plays a pretty important role because the sun is always putting out these high energy particles that come racing towards the Earth in the solar wind, and these are high velocity charged particles, and they will get entrained up into the Earth's magnetic field and basically are deflected around the Earth's magnetic field. Because of that magnetic field, those particles don't strike the Earth, which could be very bad for, life on the planet Earth. So you have a little video. This is a video. It causes a magnetic substorm that generates the aurora borealis. If you get these high energy particles that enter into the Earth's atmosphere, as they interact with the atmosphere, they produce a particular type of radiation called Wyckoff radiation, and it will create these sort of pretty lights. There's not that much of these particles that actually get into the atmosphere, but the little bit that do, they create the aurora borealis. Ever seen the aurora? We don't get it down here because the Earth's magnetic field, if you notice, it goes into the high northern or the low southern latitudes. So you just don't get any high energy particles that enter into the middle latitudes. Let's watch this video. I have a couple to show you. One is it's just like a simulation of these high energy particles coming into the Earth's magnetic field. And it's going to show actually how these high energy particles, they can sort of get linked to the magnetic field and they'll strip it away and curve it backwards, and then these particles come back and go into the Earth's atmosphere. So let's see. And then I'm going to show you another one about a solar storm. I think this is it. All right, let's review our cross product. We'll have to do this for the next exam, where we'll get into this next time, but determine the force on a charged particle as it enters a magnetic field. We'll have to know how to do the cross product. This is sometimes called the vector product. The result of the vector product is the product of two vectors. And the reason we call it the vector product is that the result of the cross product is a vector. Well, the result of the cross product is orthogonal to both of the vectors. And orthogonal just means that it's perpendicular. So like, for example, I have my x and my y-axis, they're perpendicular, and then the z-axis is also perpendicular to both the x and the y-axes. And so we'll talk a lot about our right-handed coordinate system. The coordinate system is an orthogonal system. It's always perpendicular to every other, both of the other axes. The z-axis is orthogonal to the x and the y. The x is orthogonal to the z and the y, and on and on. So the magnitude of the cross product is equal to the area of the parallelogram bordered by the two vectors. So if I imagine that I have these two vectors, A and B, and I want to know the cross product of A and B, then the magnitude of it is just going to be the area of this parallelogram that's traced out by the two vectors. All right, the direction of A cross B will be here, and the magnitude will be given by the area of that parallelogram. And so we can find the area of that parallelogram is given by this BA sine theta. So our area is given here. And so in a similar way, if we want to know the magnitude of our cross product, it's going to be equal to AB sine theta. Listen, our cross product, if you remember the dot product, the purpose of the dot product was to take two vectors and in the same direction and take the product of them. The purpose of the cross product is going to take two vectors that are perpendicular to one another Now we use the dot product for work because a force in the same direction as displacement created work. But we're going to use it for, we'll use it before for torques, the cross product, because we were looking for the force that was perpendicular to the moment arm. All right, so our cross product will take two vectors that are orthogonal to one another and take the product of them. So it's the product of one vector with the component of another vector that's perpendicular. So if you imagine this, this is our first vector, and then this is that vector that's perpendicular. And that's why we have that sine theta term, because it takes a component of that second vector that is perpendicular. So if you imagine that A is in the x direction, then this will be like the y component of B. Right? Again, you imagine that A here is in the x direction, and if you have B here, where this is theta, then B sine theta will be here. And so we're taking the product of this vector with this vector that are perpendicular to one another. We use this for torques, but we'll use it for magnetic fields as well. Let's just do a quick example. Let's say that I have two vectors, A and B. A is going to be AXI plus B, or excuse me, plus AYJ. I'm not going to do the K term here, but you can add it in if you like. This is going to be BXI plus BYJ. And then if I want to take the cross product, it's going to be AX plus AY, excuse me, AXI plus AYJ crossed with BXI plus BYJ. And then I just use FOIL to expand that product. And so A cross B is going to be equal to AX BX, I cross I. All right, that's the first. Outer is going to be AX BY, I cross J. Be careful that you get the order of the terms correct, because if you switch the order of the terms, it switches the sign. We'll see that in just a bit. Inner is AYBX, J cross I, and last is AYBY, J cross J. All right, but if my cross product, remember A cross B is equal to AB sine theta. If I have two vectors that are in the same direction, what is the angle between them? What is the angle between I and I? It's 0. So I times I has a magnitude of 1. So it'd be like 1 times 1 times the sine of 0. That I cross I term is going to do what? It's going to go away. It'll be 0. So I cross I is going to be 0. Likewise, J cross J will be equal to 0. So anytime we're dealing with two unit vectors that are in the same direction, we just won't write those at all. So these terms go completely away, here and here, and I'm just left with these perpendicular terms, I cross J, J cross I. We're going to use the right-hand rule. You might have learned how to do cross products a little bit differently in Calc 2, Calc 3, whenever you learned it. But we use the right-hand rule. There are a couple different ways to use the right-hand rule. I like to let my index finger go in the direction of the first vector, and then my middle finger go in the direction of the second vector, and then your thumb gives the resultant, the cross product. So for example, if we wanted to do I cross J, so let the index finger of your right hand, not your left, go in the direction of the first vector, and the middle finger go in the direction of the second vector, and then the thumb gives the direction of the cross product. So for example, if I have I cross I, I'm going to draw my coordinates over here. I have I here, that's my X, J here, that's my X, K, Y, and then K is my Z. If I'm doing I cross I and J cross J, we've already said those are 0. But if I do I cross J, I'll let my first finger go in the direction of I, middle finger in the direction of J, and then my thumb is the direction of the resultant. So what is I cross J equal to?
Okay.
It's equal to positive K. Right, so this has to be plus K. And if I flip it and do J cross I, this in the direction of I, this in the direction, this in the direction of J, this in the direction of I, and then my thumb now goes into the board. So that's going to be in the K direction, or the negative K direction. That's the thing about cross products too, is that they are not, what is that, commutative? When we say AB is equal to BA, they do not have that property. So if I have A cross B, that's equal to the negative of B cross A for cross products. They are not commutative like scalar quantities are. Okay, so then my cross product is going to be AX BY minus AY BX times K. All right. Don't sweat it if you're not getting that. We'll do some examples next time, and you'll get it by the end. It's really actually pretty simple. The right-hand rule can be a little confusing, but you'll get it just fine. Let me show you one other thing. We're going to use plus and minus z direction quite a bit, plus and minus k. And so to denote the negative z direction, we're going to use a symbol that looks like this. It's supposed to look like an arrow going away from you, like the fletching of an arrow. And what does an arrow look like if it's coming towards you? You have an arrow coming like right at your face? No, that's probably good. It's going to look like this, just like the point of an arrow. Or sometimes we'll have a region, and we'll put a bunch of X's to show a magnetic field in a region, or just single dots to denote a region. All right, next time we'll get into magnetic fields. I do want you to take out a sheet of paper. I like to do sort of midterm assessment class, not for y'all, but for me, because y'all do evals at the end of the semester. But if you can just take out a sheet of paper and just write one thing that you like and one thing that you would change about the course. No need to put your name on it.
Yeah,
One thing that you like and then one thing that you would change about the course.